So here on the two first slides, I give you some websites where you can go and have some more explanation, but also some exercise to train. And some of them are very simple. It starts from the very beginning, and you can train, and you have also explanation and the solution. So it's very easy to use and to train. Here is the book from which I get some exercise also, but also some explanation. You also have some NMR table for proton and carbon-13. So you can go to these books and train also. So what is the aim of my lecture today? It's trying to explain what is the NMR phenomenon. So it's a NMR for nuclear magnetic resonance. We will try to see how it works, but or where does it come from, but with very simple explanation. And we will try to understand how we can use extract the informations to get the structure, the final structure. So what is nuclear magnetic resonance? As you could see, it's some wave, just like radio frequency, VHF frequencies, TV broadcast frequencies. So it's not something it's not dangerous for health. As you could see here, it's just like between microwave and radio frequencies. So as it's used frequencies, we can characterize the phenomenon with an energy level, and as you could see, it's like every time it depends on the velocity and the wavelength of this wave. So this is important for understanding the phenomenon, NMR phenomenon. So when you get a spectrum, it looks like this or this. And as you could see, it depends, it is directly related to the chemical structure. So we will try today to understand what is the difference between this spectrum and this one. Of course, it's directly linked to the chemical structure, but we will try to understand why sometimes we have only one line and sometimes we have several lines, and how we can use this information to go to the structure. Are you okay?
Yes, we're okay.
Yeah, okay. So NMR spectroscopy is based on the spin phenomenon. I don't know if you remember your bachelor lectures on physical chemistry, but when you describe an atom, you have many parameters, and one is the spin number. So this spin phenomenon is based on the electrons and the nucleus, but NMR will be related to only some atoms, because all atoms doesn't have a spin number. But for having NMR spectroscopy, we will need we will be able to observe only atoms with the spin number. As you know, the atom is characterized. This is the letter characterizing an atom. You know that we have atomic weight and nuclear charge. These are the two numbers linked to the atom. So depending on the value of atomic weight and nuclear charge, we will be able to have NMR or not. So the first case is when the atomic weight is odd, and then you will have a spin number, just like phosphorus. The spin, the atomic weight is 31. So we will be able to have the NMR spectrum for the phosphorus. If the atomic weight is even, then it will depend on the value of the nuclear charge. If the atomic weight is even and the nuclear charge is odd, then you will have a spin number, just like nitrogen 14. Then as we have one even and the other odd, then we will have NMR spectrum for the nitrogen 14. But if both atomic weight and nuclear charge are even, then we don't have any spin number, no magnetic properties for this atom, just like carbon 12. So we will not have any NMR spectrum for carbon 12, but we will have for carbon 13. Okay? So this is important to have NMR phenomenon. We need to have magnetic properties, and these magnetic properties are directly linked to the nature of the atom, and this is linked to the atomic number and the nuclear charge. So when the atom has a spin number, remember the nucleus is like a ball, and it goes round and round around an axis. And because of this movement around this axis, the charge in the nucleus will generate an electric field, will generate a magnetic moment. Then, and this is because we have a spin number, I repeat. Because of this, the nucleus could be considered as a magnetic bar because it has magnetic properties. So in a molecule, each atom or each nucleus will behave if as a magnet if the spin number is not equal to 0. And an NMR will be NMR spectroscopy will be able to show out these magnetic properties for each atom. And we will try, it gives some signals, and these signals should be interpreted to go to the structure, chemical structure. So to better see why this spin number is important, I show only this equation, physical equation, where you see that the value of the magnetic field, magnetic moment of a nucleus or an atom will depend directly on the value of the spin number. So if I is equal to 0, that means that both mass number and atomic number are even. I equals 0, we don't have magnetic properties because the magnetic moment is equal to 0. But in the other case, we could have magnetic properties and we can get mass NMR spectrum for this atom. So here you will try to check and we see already that we don't have magnetic field and NMR spectroscopy for carbon-12, but we will be able to have this for carbon-13, for the proton, for the nitrogen 15, and not for the deuterium. Okay, is that okay for you?
Yes. Okay.
So
it's okay.
you will not, yes, you will not be for the exam. I just explained already. You will not have any question on this part. Okay, it's just there to understand why we have when we have NMR spectrum and when we don't. So here another slide to see again the different case for the different atom. The more frequently analyzed are proton and carbon-13 for organic chemistry, natural compounds. But when you work on peptide, proteins, and so on, usually people analyze phosphorus or nitrogen also. But you see that the most frequent abundant atom, like carbon-12 or oxygen, we don't have any I number, so we won't have any NMR spectrum for this atom. So as I said, because the I number is different to 0, we have the atom is just like a magnet. It has a magnetic moment and it will behave like a magnet. But as used to say, let's forget about this. If you have a magnetic bar in your hand alone, you will not be able to see if it is a magnet or not. You need to put another magnet close to it and see if you have an attraction between the two bars or if they go to the opposite side. And then you will show out that you have a magnetic bar in your hand. For the atoms, it's the same thing. The atoms that have a magnetic moment, like this one, if it is alone like that, you don't know that it is a magnet. But to get the first step to get the NMR spectrum is to put your sample, the atoms, in a magnetic field. And the first magnetic field depends on the machine you use to get the spectrum. And the power of the spectrometer is characterized by the value of this magnetic field, which is called B0. Okay? So when you put your sample in the machine, then you start the experiment, you apply this magnetic field, this first magnetic field, and then you will reveal the magnetic properties of the atoms. And they will behave like magnet. And depending on their characteristic, they will be split in two energy levels depending on the orientation of the magnetic moment. So when the spin number is equal to 1/2, then you will have two energy levels. And each of them will be characterized with an energy level. And if we stop here, this is the only thing we can see. We don't have any resonance yet, okay? We just have a distribution of nucleus on two energy levels. If we want to have the resonance, which is called the nuclear magnetic resonance, we need to apply a second external magnetic field, which is called B1. This is the true population of nucleus when we apply only B0. So in a sample, just see like that, in a sample, when you don't apply any external field, magnetic field, we have anarchy. The nucleus have different kind of orientation. The magnetic moment have different orientation. But when you apply B0, you put the sample in the machine, then you see that we put some order in the sample. Some of them will be oriented in up in the same direction than B0, and the other in the opposite side. So we have two energy levels. If we want to have the resonance, then we will need to apply another magnetic field, which is called B1. And when we apply B1, then we will have exchange between the two energy levels, okay? And the value of B1 should be at least equal to the difference of energy between these two levels. And then when we add this, then we will have some movement. Some of the upper level will go down to the lower level of energy, and some other from the lower will go up to the higher level of energy. And when you have many nucleus in the sample, usually it's like in nature, you will have more sorry. You will have some more nucleus in the lower level of energy here. And I try to find can I write? No. you will have more nucleus with the lower level of energy than those with the higher level of energy. So when you will apply B0, you will have more, a little bit more nucleus going up than those going down. This is a little bit more complicated. So it's just like this. So you will have some the global results of the exchange between these two levels will depend on these small amount of nucleus that are in the lower level of energy. So that's why we used to say that NMR spectroscopy is an absorption technique or a spectroscopy of absorption, because we absorb, the nucleus need to have energy to go to the upper level. And the absorption is a little bit higher than the emission. Remember, when you go down from the upper level of energy to the lower, you lose energy, but when you want to go up, you need to absorb energy. So that's why we say that NMR is an absorption technique, spectroscopy. And this phenomenon, this exchange between the upper and the lower level, this is called the resonance phenomenon. Okay. And this phenomenon, this resonance, is only based on the small amount of nucleus that are in the lower level of energy. So as it is based on this lower number of nucleus, that's why we need a machine or a computer to increase the signal that we detect, because the signals is very weak. So we talk about this already. So in conclusion for this part, theoretical part, to have the NMR spectroscopy, we can observe only nucleus that have a spin with a spin number that is different to 0. And for example, proton, carbon-13, and so on. We will talk only about proton and carbon-13 in this lecture. The first step to reveal the magnetic properties, we need to apply an external magnetic field, which depends on the power of the machine, which is B0. The higher B0 is, the more sensitive is the detection of the NMR phenomenon. So this first magnetic field will generate or will make the distribution of the nucleus between two levels of energy, and a second external field, which is called B1, will depend on the frequency, and so the energy level, the difference of energy level between the higher and the lower level, and this B1 will generate the exchange between these two levels of energy, and this is called the resonance. And this phenomenon, the resonance, is directly linked to the frequency. So we called about frequency of resonance. and this frequency for one nucleus will depend on the other atom to which this atom is linked in the molecule, in the structure, in the chemical structure. So when we will try to analyze the spectrum, on the spectrum we will have signals depending on the frequency of resonance. And if we can understand and interpret this frequency of resonance, we will be able to go to the structure, the chemical structure. And of course, the value of B1, just what I said, depends on the element first. We will not have the same how do you say that, interval of frequency if you want to observe proton, or if you want to observe carbon-13. You will choose the value of B1 because proton and carbon-13, for example, doesn't have the resonance at the same frequency also, okay? So when you want to observe proton, you will observe only protons. You will not, on the spectrum, you will not have the carbon-13, and the same thing, if you observe the carbon-13, you will not see signals for proton, and so on. So how do we get the spectrum now? When you you put the sample in the machine, you apply B0, then you apply B1, and if in your sample you have only one nucleus, one atom, for example, one proton, we will have something like that. The detector will register this signal, which goes up and down, and the signal will decrease in the time. So this signal is called free induction decay, FID, and the interval between each peak depends on the frequency. So if we have, so this is for one nucleus, and of course, in a sample, you will have many of these kind of signals with a different space between these peaks, because the frequency of resonance of each nucleus will be different. So it will be very difficult to interpret something like that. So that's why we have a treatment, computer treatment, which is called Fourier transformation, FT in English, TF in French. And if we work only on one nucleus, this FID will give this kind of spectrum where you have a scale of frequency, and then you have one signal corresponding to this nucleus. But in a sample, you will have not only one nucleus, you will have many of them. So it's something like that, very confusing. But after treatment, the transformation, the Fourier transformation on each FID, then we will be able to have this kind of a spectrum. Again, we have the frequency, the scale of frequency, and on this we will have signals at different frequency of resonance. That means that these groups of protons, for example, do not have the same place in the structure, the chemical structure, and then we will try to analyze why they are different and how I can place the atom in the chemical structure depending on their frequency of resonance. Okay?
Okay.
Do you have any question on this at this point? No? So an NMR spectrum will look like this, with a scale of frequency which goes from the right to the left. The 0 is here, and we go up to the when we go to the left. So the machine, this is how it is in the machine. Here you have the sample in a tube. This is a big magnet in the machine, which will generate the value, the magnetic field, the first magnetic field B0. And around the sample, we will have some electric wires which will generate the magnetic field B1, depending on the nucleus we want to detect. The computer will change the value, we choose the value, and then we can observe either the proton or the carbon-13, for example. And associated to this, to the detector, we have the recorder, which is the computer, and we work on the computer to make the transformation Fourier transformation, and to get the spectrum, final spectrum. I don't know if you have already the opportunity to enter in a room with the NMR spectrometer. So it's something very big. You see the scientists here, and the size of the machine depends on the power of the machine. Of course, the higher the B0 is, the bigger the machine is, of course. So inside you have the big magnet which generate B0, and you add your sample from the top. It goes in the machine here, and this is the probe which will generate B1 depending of the nucleus you want to observe. So let's go now finish the theory. So we go now, we enter in the NMR spectrum, and we try to understand how we could interpret the different kind of signals. So here we start with a very small molecule here. You see we have an aromatic ring here, a CH2 linked to an oxygen, then to a C double bond O and a CH3. This is an ester function, okay? So when we register the NMR spectrum for the proton here, we are able to get this spectrum, and starting from 0 here, we have a first signal, a second one, and a third one. Here we, if we don't ask the computer anything, the Fourier transformation will give us a spectrum like this with a scale of frequency. But so it's expressed in hertz. This is not ethyl acetate. This is wrong. I have to change this. So this again to understand that we apply B0 and it will depend on the value of the frequency of resonance. And the frequency of resonance will depend on the nucleus and its place in the molecule. But sorry. So when we express the results in frequency, you will have to precise each time what is the power of the machine you use to get the spectrum. So you will have to say, well, this proton has this frequency of resonance on the machine with a B0 of let's say 100 megahertz. And if you do the analysis in Vietnam on one machine with B0 of 100 megahertz, and me here in Lyon, I will do the same analysis, but on another machine with the 200 megahertz or 100 megahertz. I will need to precise what is the value of B0 because the value of the frequency of resonance will be different. So if we stay with the frequency, the scale of frequency, it's very difficult to compare the results between scientists because we don't work on the same machine everywhere. So to homogenize the results and to be able to compare the results in the world, we calculate the scale in another way, and we transform the frequency in chemical shift, scale of chemical shift, which is symbolized by the letter delta. And the unit is ppm, party per million, and it comes from hold on. It's comes from the division of the frequency of resonance of one peak divided by the frequency, the value of B0 in megahertz. So that's why, and we cross by 10 power 6. So that's why we talk about party per million. Okay? So when you do so, you don't need to say what is the power of the machine you use, because the ppm is something international. So we can compare the value between different kind of machine. The value will be the same, quite the same on a 100, a 200, or a 90 megahertz machine. So we will use this scale starting from now. So what is the chemical shift, and it is different when we compare one atom to another? Parts per million. So how it works? So if we have one proton only in the sample, we apply B0 and then we apply B1, and we will have only one peak on the spectrum. Okay, one proton gives one peak. Donc we don't need this. But if we have more protons in the structure, then we will have many peaks or in the spectrum. The number of peaks will depend on the number of group of protons in the structure. So we can use some table with the standard value that can give us an idea of the chemical groups in the structure. And then, for example, we can see that methyl group, the protons of the methyl groups always have a frequency of resonance around 1 ppm. If we are in an alkane, something very simple. But if the methyl, for example, is on the carbon wearing an oxygen, then the chemical shift will be a little bit increased, higher, 1.5 ppm, and so on. So you can see on this table that depending on the chemical groups or the heteroatoms, that double bond or triple bond you have in the structure, then the protons or the carbon will not have the same frequency of resonance, and so the same chemical shift. So that's why we have to learn to use and to work with to be able to interpret NMR spectrum and to get the chemical structure. So as you could see here, we have a scale of proton. And in proton, the scale goes from 0 to around 12 ppm. And this you should have to keep it in mind. And we can make some slice. Let's say that in an alkane, the protons are around 1 to 2 ppm. When you have proton close to a double bond, it's around 2.5 to 0.8 ppm. If the proton is on the double bond, you see you are around 5 to 6.5 ppm. And aromatic protons on aromatic rings are from 6.5 to 9 ppm. And what is important also is proton on heteroatoms will have a resonance on a wide range of frequency, depending on the chemical groups you have, for example, on the aromatic rings or on the aliphatic molecules. So you could see here that even, for example, if you have an heteroatom close to the proton, then you see that even if it is a CH2 or it could be a CH3 also, you will not be here around 1 ppm, but you are here around 3.5, as you could see here, 4 ppm. So that means that depending on the electronegativity that there is around the protons we are observing, then you have a change in the frequency of resonance. And because of this change of frequency of resonance, we will be able to say that we have in the structure an heteroatom close to this group of protons, because we have a chemical shift around 4 ppm. Okay,
Okay.
Yes, yes. Okay, what time is it? 11. So here again, the same relationship between the frequency of resonance of a nucleus, an atom, and the frequency, the strength of the machine. And this is again the scale, just to see that aliphatic protons will be observed between 0 to 5, and between we have we can have double bond here, oxygen close to here, nitrogen here, for example, and up to 5 you have usually proton on double bond. So in ethylenics, it's around 5 to 6.5, and up to 6.5 until 9, you have aromatic protons. So this phenomenon, we can describe, I need to charge my computer, excuse me. So to describe the spectrum and the place of the signals on the scale, we can use some vocabulary. We talk about shielding or de-shielding phenomenon, depending when we want to compare, for example, two groups of protons. We will say the first one is shielded compared to the second one, or these groups of atoms will provoke a shielding effect or a de-shielding effect depending on the nature of the chemical groups. So when close to the proton, for example, we have a chemical groups that gives a proton. We talk about electron donor effect. Then the chemical shift will goes down. So we talk about a shielding effect. On the contrary, if you have a chemical groups that withdraw electrons, just like a double bond with an oxygen, for example, then the chemical shift will goes up, will increase. Then we talk about a de-shielding effect. Okay, it's yeah, sorry. So how it works here on this table, you see that we compare the chemical shift of the proton of the CH3 here, depending on the substituent on the close to the methyl group. Okay. Here are the electronegativity of the substituent, and you see the electronegativity decrease. And here is the evolution, the change of the chemical shift. So if we start here from the methane, CH4, the electronegativity is very low, 2.2, and the value of the chemical shift of the CH3 in, well, the protons in the CH4 is very low. Remember, I told just before that the methyl in aliphatic structure is around 1 ppm, and then you see in the methane it's lower than lower. it's around 0.23 ppm. So this is, let's say, the reference of the aliphatic protons. Then if you add on the structure, you change a proton in an iodine atom, then the electronic activity of I is 2.7, and you see that you have an increase of the chemical shift to 2.16. And the higher the electronegativity will goes, then the higher the chemical shift will go also. That means that if the X atom here or group here will be electronegative, this atom or group, functional group, will withdraw the electrons around the carbons to these groups, and then we can say that here we have a delta minus charge. This effect will be transmitted to the electrons between carbon and protons, and then we will have also a withdrawal effect to the carbon, and then the charge on the proton could be said to be delta plus. Okay, so we have a lower electronic density around the proton here, and then the consequence will be an increase of the chemical shift. We say that we have a de-shielding effect. Okay, so when we compare groups of proton, if I compare the methane, for example, and the methanol here, I can say that the protons in methanol are de-shielded compared to those in the methane, because the chemical shift here is higher in the methanol. And this de-shielding effect is directly linked to the electronegativity of the group, chemical group here, which is the alcohol. Okay? So the de-shielding effect is due to the electronegative atom or chemical groups structure. So when you look at the chemical table, Mendeleev table, you know that when you go at the horizontal way, you have an increase of electronegativity, and when you go from the top to the lower, the top and the lower size of the table, you have a decrease effect of the electronic activity. So what it's interesting for us, it's when we look at here the carbon, the oxygen, and the hydrogen here, and all the other atom can have an effect on the chemical shift of the proton, for example, or on the carbon, depending on their electronegativity. So let's do this small exercise. So we start from this molecule. This is the reference. It's the ethylene. Let's say that the value of the chemical shift of each proton there is the same. Let's say the value is delta. And you can see that here on the left side, you have another structure, another compound with an methyl ether group here. And then you see that the chemical shift on these protons is lower than in the starting molecule. It's lower than of 1.43 and 1.29 ppm for this proton. And on the other side, we have this other molecule where you have a methylcetone, methyl ketone on the structure. And then you have here an increase of the chemical shift of 0.29 and 0.22. So how can we explain that it's the difference between these three molecules? We can explain because of the electronegativity of the chemical groups of the substituents on this structure. So remember, as soon as you have a donor effect, which could be an inductor effect or a mesomeric effect, then you will have a shielding consequence on the chemical shift, which means that we have a lower chemical shift than the one in the starting molecule. And this is the case in the molecule from the left side, the ether. Remember, the oxygen has two doublets of electrons, 3 doublets of electrons here. And as these doublets are conjugated to the double bond, then we have a donor effect, a mesomer, an inductor effect, because the carbon is less electronegative than the oxygen. But you have also a mesomeric effect due to the doublet of electrons on the oxygen. So we have a strong donor effect of this group to the structure, but to the atom, and also, of course, to the 2 protons here on the structure. So we have a higher density of electrons around the protons here. And that's why we have a decrease of the chemical shift. On the opposite, when we have acceptor effect, which could be inductor or mesomeric effect, we will have a de-shielding phenomenon. For example, here on the right side, the ketone, as the oxygen is more electronegative than the carbon, we have this mesomeric effect, which is directly conjugated with the double bond. So we could have this mesomeric effect, and the consequence on the proton here is that we will have a withdrawing effect of the electrons of the carbon protons bound, and then we will have a decrease of the electron density, electronic density around the proton, and then we will have an increase of the chemical shift. Is that okay for you? Hello? Hello?
Yes.
Is it okay?
Yes, it's okay.
Okay. So this is why it's important to have in mind the classical value in the table. This is the value of the table when you go back to the no. When you go back to the table here, the CH2 is the molecule of in the middle is here. You know that you should find something. If you have no substituent, you should find a chemical shift around 6 ppm. But as you have something higher, you could say that you have a substituent on the double bond, and this substituent has a withdrawing effect. So that's why the chemical shift is higher than the theoretical value that we have in the table. Okay. And as you might remember of your first bachelor courses, lectures, inductor effects are lower than mesomeric effect. So if we have only, if we could have to compare a mesomeric effect to an inductor effect, we will have a change in chemical shift lower for inductor effect. So how can we get this from a spectrum? Go back to the spectrum I showed you before. Then for this molecule, it's benzyl acetate. Then we can see that when we look at the structure, we have one group of proton, a CH3, a CH2, and the protons of the aromatic ring. So if we have in mind the table, we could anticipate the shape of the spectrum and just thinking that as we have aromatic protons, I should have a signal around 7 ppm. A methyl group usually it's around 1 ppm, but here I have an ester function. So the ester, we just see that it has a withdrawing effect. So the chemical shift of the methyl should be a little bit higher than 1 ppm. And the CH2 here is between the effect of the aromatic ring and the effect of the ester group, but the effect of the directly linked oxygen here. So I can observe 3 groups of proton on the spectrum. 3 groups of proton. Each of them has their own chemical shift. These chemical shift depend on the chemical groups close to them. And as it is a methyl, I can say that the lower chemical shift correspond to the proton, the higher, around 7, correspond to the aromatic ring, and in the middle it might be the CH2. So the chemical shift is depending highly from the neighboring groups in the structure. So even if we don't know the structure and we have only the spectrum, if we have the NMR table, either in mind or in hand, then we can start to interpret the value of the different signals. So this is the first information we can get from either a proton or a carbon-13 or whatever the nucleus you observe. It's the first information. You can say that I have some aromatics or some functions in the structure that change or increase or decrease the chemical shift of the groups of protons. The second information we can get from the protons is, as you could see, always on the same spectrum, we see that some signals are higher than others. These signals, this fact is directly linked to the number of protons in the group, which has the same chemical shift. Here, it's just like in HPLC. We can measure the surface under the peak, and the value of this surface is directly depending on the number of protons in the group. So here, if we make the ratio between each surface, we will see that the lower we calculate how many times we have the surface of the smaller signal in the others, and we can say that here we have 1.5 times more protons here and 2.5 more protons here than in the smaller signals. So we can say that the integration, this calculation, the surface calculation, is called integration. And it can figure on the spectrum with these curves, sort of sigmoid. But we can also get only the value of the surface, also direct value, and we make the ratio between them to know how many signals how many protons we have in the group. So how to use these curves? Then we can make the difference in centimeters. We look at the wide between the lower level and the higher level. And this value is directly linked to the number of protons in the group. Okay, so this is the second information. We can get the number of protons in the group when we compare the surface of under each peak. There is a third information we can get from a proton spectrum, is what we call the effect of the spin-to-spin coupling. So what is this? Here we have two structures. This is the first spectrum we work with. We know now how to interpret the value of the chemical shift. We know how, using the surface under the peak, to know that we have 3 protons here, 1 proton here, 2.5 protons here. How can I go back? I just would like to come back and try to write on this slide, but I can't. Ça, je peux. Ah, okay. Okay, so let's go back to the integration. I just want to show you how to use it in the spectrum analysis. So as I said, these curves represent the surface under the peak. So we ask the computer to calculate this value. And the computer will draw these curves on the spectrum or give you the value here. Usually it's written 1 point, let's say something like that. And for each peak you have a value like that. But what we can do if we use these curves, we will calculate the difference between this and this, and the high here will be compared to those in the other signals. And if we do so, we will see that we have 2.5 times this high in the signals of the aromatic signals, and for, sorry. And for this, let's say here 2.5 times. If we say here it's 1, and here if we make the same, we will see that it's approximately 1.5. How can I interpret this? That means that if I say that this high corresponds to 1 proton, then I should have 1.5 proton in the left and 2.5 to the right, and 2.5 proton in the aromatic ring. Of course, it's not possible to have half protons. So that means that in the signals in the middle, it's not corresponding to 1 proton, but to 2 protons. So that means that here on the right side, I have, where is the, oh, I lost, oh. I have 3 protons here. And here I have 5 protons. So only with with the integration calculation, we can say already that we have the number of protons I have in each groups. The value of the chemical shift has told me I have an aromatic ring, I have a methyl group here, and I have a CH2 with something here and here that withdraw the electron because I am higher than what I should have for a CH2 in an aliphatic structure, it's around 2 ppm usually, but here I am higher. So the structure is coming closer. We are coming closer to the structure. So now there is a third information that we will learn to use, is the shape of the signal. I mean, here I have one line, only one line here, and only one line here. So what does it mean? So this is what I call how to use the shape of the signals correspond to understand what means when we don't have only one line, but when I have like this, something with many lines. Why I have 4 lines here, why I have 3 lines here, why I have only 1 here. What does it mean? And as you could see here, it depends directly on the type of structure. Here you could see that each group of proton is separate to each other. Here I have one group, and another group. And here I have a quaternary carbon. I have something like that. The CH3 is here. And here so I have okay, on this CH3. Here, the carbon here doesn't wear any hydrogen. It's just like we have a wall separating the methyl to the CH2. This is a big hole. And for the CH2 and the aromatic ring, we have also a quaternary carbon here. There is no hydrogen on this carbon. So it's like I have another wall separating the CH2 to the proton of the aromatic ring. In these second molecules here, I have a wall again, separating this proton to the other, but the 2 others are directly linked one to another. They are close in the structure. So we have an interaction between these groups of protons. The one which is alone is again only one line, and the other that are close together, they are different. The signals is splitted in different lines. So this is what we call the coupling phenomenon. As soon as 2 groups of protons are close together, just like this, then we can say that we have a coupling effect. Remember, this is a magnet. Let's say I have a mu value. Here I have another one. We have 2 magnets that are interacting one on another. And this interaction is characterized by a splitting of the signals depending on the number of protons in the group here. So how to use this new information? As I said, what is the coupling? The coupling here, we talk about coupling interaction transmitted by the electrons of the chemical bonds between protons. We have two protons. This is CH. And as the protons are closely related because they are on two carbon linked together, we say that this proton is coupled to that one because the electrons of the bonds here transmitted the magnetic effect from this proton to this other one. And this is called the coupling. The coupling is the interaction transmitted by the electrons of the bond, the chemical bonds. So to be transmitted, it is needed to be closely related. So that's why if you have a wall here, a quaternary carbon, for example, an heteroatom, for example, and so on, you will not have coupling between this proton and the other protons that are on the other side of the wall. And this coupling effect will depend on the number of protons on the neighbor and the value of the I number. Do you remember? But here, let's say that I equal 1/2 because the spin number of proton and carbon 13 is 1/2. So the value of the number of lines in the signal is called the multiplet in English. And the number of lines in the signal will be directly linked to the number of the number of protons on the neighborhood. So we can say that if I equal 1/2, then M equal N plus 1. That means that if you have 1 proton on the neighbor, then you will have 2 lines. If N equal 1, you will have 2 lines. If N equal 2, you will have 3 lines, and so on. Okay? So let's see on an example. So we start from here. First step, we don't have any protons on the neighborhood. Okay, this is the molecule here. The proton, it's an aldehyde group. It's on the CO. Here I have no protons on the structure. We are in the case of the first molecule we work with. We have a wall here, and we have no protons around. So we have only on the frequency of resonance or the chemical shift, I have only one line, N equals 0, M equal 1, so I have, it is called a singlet. I have only one line, m equal 1. I have a single. If I go up to the next molecule here, I see that in the structure, the same protons, aldehyde protons here, is close to a carbon where I have one proton. When I look at the spectrum, I see a chemical shift or a frequency of resonance for the aldehyde group. And I see the second protons in the structure, which is on an aliphatic carbon with 2 chlorines. So it has it's a proper chemical shift. The integration gives me a signals corresponding the same value to each signal. So I have the same number of protons in each of them. And as I say, the aldehyde group is closely related to these new protons. Then Mn equal 1, M equal 2 line. This is called a doublet. The 2 lines has the same high. Okay, we have the same high. Now it's, if I go up, next level here, I look at the structure. Well, we can start from the spectrum. I see the aldehyde group proton has 3 lines. The integration is still 1 proton, but on the other side of the spectrum, I have another signals which have 2 lines, and if I look at the integration, I have twice the high of the first one. So I can say that I have 2 protons here if here I have 1 protons. And as you could see in the structure, here I have the aldehyde protons, which is directly linked to 2 protons. So N equal 2, M equal 3. I have 3 lines in the protons. Okay? In the aldehyde, for the aldehyde protons. And as you could see in a triplet, we have 2 small lines, and in the middle, the lines is twice higher than the 2 first around. And again, high level, here I look at the spectrum, I see that the aldehyde group has changed again. We have 4 lines, integration still equal to 1, but on the spectrum, on the other side, I have another signals, a doublet, 2 lines, integration equal 3, so that means that I might have a methyl group, CH3. And this CH2 is closely related to the protons, the aldehyde group, because it's a doublet. Okay, yeah. So if I consider the aldehyde group, I see we have 4 lines. If I have 4 lines, that means that on the carbon, on the neighborhood, I have 3 protons. M equal 4, I have 4 lines. This is called a quartet. But if I consider these signals, the methyl group, I know it's a methyl because the integration is 3. And the chemical shift is around 1 ppm. And when I look at the shape of the signals, I see 2 lines. If there is 2 lines, that means that on the neighborhood of the methyl group, I have only 1 protons. 2 lines, that means that I have 1 protons on the neighborhood. It's a doublet, okay? So this is the third information I can get from a proton spectrum, is looking at the shape of the signals. Do I have only 1 line, 2 line, 3 lines, and so on? And from the number of lines depend the number of carbons on the neighborhood. Another information is important is the space between 2 lines. The difference between 2 lines, or the distance between 2 lines. This is a value, we can calculate this. Remember, we have a scale of frequency at the beginning, so I have a frequency here for one peak. For each peak, I have a frequency of resonance. So when I make the difference, I calculate the difference between 2 lines, I have a value here, which is called the coupling constant. And this coupling constant is written by J, and it is expressed in hertz. So this reminds us that at the beginning we have a scale of frequency. And this value, this coupling constant, will give us information about the distance separating the protons. Remember, we said that this is coupling, scalar coupling between protons on carbons closely related. I have 1, 2, 3 bonds separating these 2 protons, 2 magnets that are interacting one to another. So this number of bonds will influence the value of the coupling constant. I'm sorry. And calculating this coupling constant will give us information of the distance that separate the protons. So this is the fourth information that we can get from a proton spectrum. Maybe we can stop here for today, because we will start something that could be a little bit long to explain.